Hey everyone, this is Bhargav Suthar, and today we will learn a new topic, recurrence relation. Now, in this today's session, we will learn what is a linear recurrence relation and what is a homogeneous solution. So first, let us discuss what is a recurrence relation. In many discrete computation problems, it is easier to obtain the numeric function form of a relation between its terms. Now, the recursive formula for defining the numeric function is called a recurrence relation. Consider a numeric function a that is set a0, a1, a2 up to ar. Then a recurrence relation on the numerical function a. It is a formula that relates all the terms of a to previous terms of a, like this: a r plus 1 that is equals to ar. Now simply just substitute values of r from 0 to infinite and we will get this a. A recurrence relation is also called a difference equation. To define the numeric function completely using the recurrence relation, the values of the numeric function at one or more points are required to initiate the computation. These given values of the function are called initial conditions. Let us discuss one example. Now, the recurrence relation for Fibonacci sequence. We all know what is the Fibonacci sequence. So, the recurrence relation for Fibonacci sequence of numbers is AR equals to AR minus 2 plus AR minus 1, where R is greater than or equals to 2, with the initial conditions A0 equals to 1 and A1 equals to 1. So, this is the formula AR equals to AR minus 2 plus AR minus 1, and initial conditions are both A0 and A1 equals to 1. So by using this formula or by using this recurrence relation, we will be able to get the whole Fibonacci sequence. So that is the recurrence relation. That means we need to apply the same formula again and again, that means recursively, and we will get the sequence. In this case, we will get the sequence. For another example, you will get some different thing. Now, thus, the Fibonacci sequence is given by this. We know that it is 1, 1, 2, 3, 5, 8, 13, and so on. How? See here, the condition is r greater than or equals to 2. We have initial condition 1 and 1. So here, both 1 and 1 are there. Now, what is the formula? Put r equals to 2. So what will be the formula for r equals to 2? That means a2 equals to a0 plus a1. And we know the initial conditions a0 and a1, and that is 1 and 1. So that means just simply add it. So 1 plus 1, so that is 2. So a2 will be 2. Now again, recursively doing the same thing. So a3, put r equals to 3. So a3 will be a1 plus a2. What is a1 and a2? a1 is 1 and a2 we have just calculated, that is 2, and the summation of that is 3. And in the same way you will get 5, 8, 13, and so on. Now, what is linear recurrence relation with constant coefficients? So suppose small r and k are non-negative integers, then a recurrence relation of the form thus C0AR plus C1AR minus 1 plus C2AR minus 2 up to CKAR minus k, that is equals to f of r, some function of r, for r is greater than or equals to k, where this all ci, that means all c0, c1 up to ck are constants, is called a linear recurrence relation with constant coefficients of order k, provided c0 and ck are non-zero. So here all these c0, c1, c2 up to ck are constants and it is of order k. How? Here see the r minus k term. So whenever this k is there, so it is of maximum order. So it is of order k. For example, the relation ar minus 2ar minus 1 equals to 2r. It is, now see, r minus k. So just compare it with r minus k. So what is k? So k will be 1. So it is a first order. It is a first order linear recurrence relation with constant coefficients, because a coefficient of ar minus 1, all are constants, so it is of constant coefficients. In same manner, ar plus 2ar minus 3 equals to r square. Now what is k here? R minus k, just compare it with r minus k. So k is 3. So it is a third order linear recurrence relation. Now see this, ar square plus ar minus 1 equals to 5. This is not a linear recurrence relation. It is a recurrence relation, but it is not a linear recurrence relation, as we have here ar square. But here it is not the case. So it is a recurrence relation, but it is not a linear recurrence relation. Next, homogeneous solutions. Consider a kth order linear recurrence relation with constant coefficients. Then this equation is the same that we just discussed earlier. C0AR plus C1AR minus 1 plus C2AR minus 2 up to CK minus K and equals to f of r. Then the homogeneous recurrence relation of the above, that means the one, is given by, now see, you can see what is the difference in both these equations. It is actually, it is the same one, but see right hand side. Then above, the right hand side is f of r, and here it is 0. So that means that for any linear recurrence relation, if f of r equals to 0, that means right hand side is 0, then the given equation is homogeneous recurrence relation. So all you need to just remember one thing, that for homogeneous, if right hand side equals to 0, then it is homogeneous linear recurrence relation. Now the solution of the homogeneous equation is called homogeneous solution. The characteristic equation of equation number 1, the characteristic equation of this, the first equation, is called the is the kth degree polynomial, and it is given by C0 alpha raised to k plus C1 alpha raised to k minus 1 up to Ck equals to 0, and where k is the highest order and these are the constants. We will just discuss it in example. This polynomial in alpha, it is of degree k, so it has k roots and it's called characteristic roots. Now let us discuss types of roots of the characteristic equation. Now let alpha 1, alpha 2 up to alpha k. Why alpha k? Because the equation or the characteristic equation will be of kth order, so there can be maximum k roots. So let alpha 1, alpha 2 up to alpha k be the roots of the characteristic equation. Now there are two possibilities: either the roots are distinct, or two equal roots, or many equal roots. We'll discuss this. So first, for distinct roots, the solution will be AR equals to A1 alpha 1 raised to R plus A2 alpha 2 raised to R up to AK alpha k raised to R. For distinct roots, this will be the solution, homogeneous solution, and for two equal roots. Now here we have just discussed only one case. Suppose there are means out of k roots, there are total two roots which are equal. So let's just name it alpha 1 and alpha 2. So A1 plus A2 R into alpha 1 raised to R. So what we are doing is, just instead of this, A1 alpha 1 raised to R plus A2 alpha 2 raised to R. So A1 plus A2 R into alpha 1 raised to R. So we are just combining it and multiply it by R plus A3 alpha 3 raised to, and the rest is same. So suppose there are three equal roots. So what will be it? A1 plus A2R plus A3 R square into alpha 1 raised to R plus A4 alpha 4 raised to R, and so on. Now let us discuss examples. First, find the solution of AR plus 2 minus AR plus 1 minus 6AR equals to 0. Now, first, see, here it is a homogeneous equation. How? Because the right hand side equals to 0. Now, first, the characteristic equation. So, here the order is 2 because R plus 2. So, just order is 2. So, the characteristic equation will be alpha square minus alpha minus the 6 equals to 0. Now, what are the factors of this polynomial? It will be alpha minus 3, alpha plus 2 equals to 0. Then, what will be alpha? It will be 3 and minus 2. So, that means alpha 1 is 3 and alpha 2 equals to minus 2. Now, we have two cases. Either the roots can be different or it can be same. So here the roots are different. That means the first case, which are the characteristic roots of the equation. So what will be the homogeneous solution? Hence, the homogeneous solution of the given recurrence relation is AR equals to A1 into alpha 1 raised to R plus A2 alpha 2 raised to R. So here we have only two roots, so we are just stopping here. So A1 3 raised to R, that means alpha 1 raised to R plus A2 minus 2 raised to R. So this is the solution. This is the solution which satisfies this recurrence relation. Next, find the solution of AR plus 2 plus 2AR plus 1 minus 3AR equals to 0 that satisfies A0 equals to 1, A1 equals to 2. Now here the given equation is homogeneous because the right hand side is 0, but we have just given here the conditions that satisfies A0 equals to 1 and A1 equals to 2. So how to do it, just we will discuss. For first, the procedure is same. The characteristic equation here, the order is 2. So what will be the characteristic equation? So here it will be alpha square plus 2 alpha minus 3 equals to 0. Now, what are the factors of this quadratic polynomial? It will be alpha plus 3 into alpha minus 1 equals to 0. Hence, what is alpha? Alpha is minus 3 and 1. So, which are the characteristic roots of the equation? Now, again, these roots are unique. So, we will apply the first case. So, hence, the homogeneous solution of the given recurrence relation is AR equals to A1 alpha 1 raised to R plus A2 alpha 2 raised to R. So let us take this as alpha 1 and this as alpha 2. You can change the order as this A1 and A2 are constants. So AR equals to A1 minus 3 raised to R plus A2 1 raised to R, where A1 and A2 are constants. So up to this we know that, but now we have given the conditions. So what is the use of this? So whenever the conditions are given, we can find these constants. So first, that means we need to find the constants A1 and A2. Now A0 is given, A0 and A1 are given. So put R equals to 0 in this equation. So what will be it? A0 equals to A1 minus 3 raised to R plus A2 1 raised to R. So that means A0 equals to minus 3 raised to 0, that is 1, 1 raised to 0, that is also 1. So A0 equals to A1 plus A2. Now A1 equals to 2 is given. So put R equals to 1 here. So A1 equals to A1 minus 3 raised to 1 plus A2 1 raised to 1. So that means A1 equals to minus 3A1 plus A2. So we have two equations. Now we can solve these two equations by elimination method. That will be the easiest one. So solving the above two equations, we will get A1 equals to minus 1 by 4 and A2 equals to 5 by 4. So now substitute these values in this equation. So hence AR equals to A1, that is minus 1 by 4 and minus 3 raised to R plus 5 by 4 and 1 raised to R, that is 1. So this is the final answer. And last example, find the solution of AR plus 6 AR minus 1 plus 12 AR minus 3 plus 8 AR minus 3 equals to 0. Oh, there are total 4 terms. Now, see first, right hand side equals to 0, hence it is a homogeneous recurrence relation. Now first, what is the characteristic equation? It will be here, what is the order? Order is 3. You can check. So what will be the equation? That is alpha cube plus 6 alpha square plus 12 alpha plus 8 equals to 0. Now the cubic equation. But actually it is a perfect cube of something. And it is a perfect cube of alpha plus 2. So that means alpha plus 2 cube is this. So alpha plus 2 cube equals to 0. Hence, what is alpha? Alpha will be minus 2, and minus 2. Now here you can see that minus 2 repeats 3 times. So in previous two examples, it was unique roots. So now here the roots are repeating. So that means we will use second case. So what will be the homogeneous solution? Hence, the homogeneous solution of the given recurrence relation is AR equals to, see here the alpha is repeating 3 times. So A1 plus A2R plus A3R square into minus 2 raised to R, because alpha is same and it is repeating 3 times. So there will be 3 constants where A1, A2 and A3 are constants. Thank you.